Hello, my name is Sam Lemaster, and today we'll be talking about the impact of computer-aided design on design engineers. Computer-aided design is used to create technical models and drawings across the engineering industry. I'm sure all of you are familiar with the concept and the technology, as it's a critical part of engineering curriculum around the world. It's instrumental in today's product development process, used not only by designers, but also by manufacturing and quality engineering. There are several benefits and drawbacks for the development of design engineers who use this technology. Benefits including improved productivity, spatial awareness, and creativity, while the drawbacks listed are design fixation and circumscribed thinking. A literature review was conducted to evaluate these benefits and drawbacks and see how computer-aided design impacts design engineers. That'll be discussed today. Before we begin discussing how the CAD impacts design engineers, it's important to understand where the technology came from. Computer-aided design was developed as a project out of MIT in the 1960s as an attempt to create symbiosis between computers and designers. The goal was not only to create a tool that will help solve problems, but help formulate the problem in the first place. As an added benefit, it would replace the tedious aspects of drafting and drawing methods used previously. As I mentioned, there are several benefits of computer-aided design for early design engineers. The first one we'll discuss is productivity and product development. So CAD helps reduce the product development timeline by enabling concurrent engineering. This concept refers to the fact that design engineers and manufacturing engineers can be working on the same models at the same time, both making design changes and preparing for manufacturing. And the changes are flown through the process and carried forth by all the disciplines. It shortens the design time while also improving the quality and the productivity of the team. CAD also allows part reuse in assemblies, which saves time and reduces the redundancy of design jobs. We'll talk more about design satisfaction in the future, but it also helps eliminate the repetitive and routine calculations associated with dimensioning and tolerancing complex parts or assemblies. If you involve CAD early enough, it can also help boost engineering problem-solving skills, because it requires you to have a clear design definition prior to beginning. You need to know your general constraints that you're dealing with and have an idea where you're headed in the future before starting. Some other benefits include creativity, job satisfaction, and what's referred to as self-efficacy. So creative self-efficacy is defined as an individual's confidence in their own creative abilities. And research has identified using pre- and post-test studies that teaching methods utilizing 3D CAD in their curriculum boost the creativity and also the confidence among design engineers. This is attributed to the ability to see the final product and sort of visualize your ideas and allow yourself to see them coming, starting as an idea and proceeding all the way to a feasible product. It also helps improve job satisfaction based on the following topics. So it allows design engineers to touch a larger number of parts and incorporate them into the assembly. So the improved productivity allows you to work on a number of different products, as well as sort of see the projects on a larger scale. When you take the bracket that you may have been designing previously and assemble it into your higher level assembly, you start to see that the work you're doing is making a difference. Additionally, there's a promoted sense of responsibility due to the autonomy in your tasks. You're no longer creating a concept and passing that along to a draftsman who passes it along to a checker, and there's less frequent interfacing with your management. You can sort of take a concept and run it all the way through in preparation for a design review before you're required to request additional work or seek guidance moving forward. That helps you own the tasks that you're working. The final benefit of CAD that we'll talk about today is the improved spatial awareness. Spatial awareness is defined as the ability to mentally manipulate and comprehend orientation in 3 dimensions. So you can visualize your concept or the product that you're working on and see how it'll fit in space, understand the relative size and proportions to other products. And this is correlated to success in engineering based on research that spans several decades. Studies suggest that training via computer-aided design improves this awareness among designers as well. That's when compared to traditional drawing coursework and uses a control group for the validity of the research. Now, like I said, there are some drawbacks to incorporating computer-aided design as a design engineer. The first of which is design fixation. The fixation describes the hesitation to deviate substantially from your initial concept layout. Iteration and revisiting your initial design is instrumental in evolving your products, as the first design is never the best. Studies suggest that improper training can drive inexperienced designers to become fixated upon completing the first revision of a CAD model. And this is especially common if there's a built-in simulation or assessment, which is common in several of the case studies we reviewed, because there's an additional step required to evaluate and justify the changes you made to your model. So it's easier to sort of stick with the original concept. It also has the ability to cause a false sense of design maturity when you develop a concept via CAD, because a lot of the rendering and visualization capabilities make it seem as if you're ready to push go and start building these products. But when you start to transition to manufacturing, or you go host these reviews of your designs with either with other disciplines or with more senior engineers, you find that you need to modify your design and things aren't quite as perfect as they seem. So that's sort of a disappointment and can cause engineers to become less satisfied with their job. But fortunately, a lot of these things can be mitigated by process improvements, which we'll discuss in the future. The final drawback of CAD we'll discuss is referred to as circumscribed thinking, and that involves constraints introduced by the complexities of the modeling software and not the complexities of the design itself. So if a user is not able to create the concept they imagined originally, they may just generate a simpler solution because that's the more straightforward path. They may be under pressures from either a schedule standpoint or from a competitive nature, and this is also referred to as bounded ideation. As I mentioned previously, this can also be mitigated through proper training and even using some more traditional means like sketching to capture concepts in a different medium before proceeding with the technological approach. So to summarize some of the benefits of computer-aided design, they're both tangible and intangible. The easily quantifiable or measurable benefits are the shortened development time and improved spatial awareness. You can look at these via examination and put numbers against the benefits that CAD offers. However, there's some less tangible aspects that are just as important, being creativity and job satisfaction for designers. So the improved performance, improved productivity, certainly boosts the morality among engineering teams and helps create a better culture in the industry or in academia. And this creativity and self-confidence is attributed to visual reinforcement of ideation. The ability to take a concept and to capture it and, as I mentioned, to render it and really visualize it to convey your message is a very rewarding process, and it helps engineers become successful. Some of the drawbacks that we discussed, there's certainly complex actions that are required to construct the novel solutions designers inherently create, and they require training and mentoring for early designers. So unfortunately, the difficulty creating these intricate shapes and modifying features leads to design fixation and sort of constrained thinking. Fortunately, the major downfalls of CAD are primarily process related. So poor training and high expectations contribute to these downfalls, but improvements are proposed on the following slides. So by optimizing CAD software packages, we can help designers overcome this learning curve, maybe by improving the graphical user interface or incorporating gesture-based controls that are common in other applications. We can improve the experience for new designers. If we introduce the topic of CAD earlier and optimize the coursework, we can also improve the experience. As teaching designers the software package early on will promote both experimentation as well as boost interest for those originally opposed to STEM roles. And if we offer intermediate steps in the design training, we can improve design habits and sort of foster that iteration that's necessary to be successful. So formal design reviews should have desktop-based predecessors with experienced engineers to promote that iteration prior to design finalization that early designers may be inclined to leap to. So as a parallel to industry, some of these recommendations are already in place. However, there's always opportunities for improvement. So design review processes at several phases of the product development already exist. However, they typically focus on interdisciplinary, big picture assessments and not necessarily the design details themselves. There are also documented training curriculums and design manuals that capture best practices and lessons learned, but they've become dated as technology advances and could certainly use updating. So to improve these industry practices, you can incorporate desktop reviews to pose what-if questions and challenge assumptions earlier in the design phase to help teach these lessons and drive early design engineers to iterate and revisit their early assumptions to produce a more robust final product. Additionally, we could expand the training curriculum across engineering disciplines, both from a technological aspect in the computer-aided design world, as well as other best practices help interface between disciplines and sort of revisit that concurrent engineering highlighted earlier. And finally, if we update the manuals to include some of these technological advances, we can help foster learning among designers. So a couple of notes on the future of computer-aided design. Optimization algorithms that are embedded in CAD and analysis software will highlight the importance of defining your interfaces and requirements up front. And additive manufacturing will allow you to bridge the gap between designs that were only theoretically feasible before and the actual manufacturing process. So designing these organic structures that optimization predicts and really continue to push the gap or the realm of possibilities there. And finally, improving those interfaces will reduce the learning curve and potentially open the doors to a larger audience. So in conclusion, CAD will continue to grow as technologies like additive manufacturing become commonplace and help push us to accelerate and meet the product needs of tomorrow. The positive benefits of CAD certainly outweigh the negative aspects. And to summarize, the benefits were the improved productivity, and increased spatial awareness and creativity, and the drawbacks were the design fixation and circumscribed thinking that we discussed earlier. So if you incorporate these outlined improvements, we'll stand the best chance to develop the design engineers of tomorrow. Thank you.